Hello, hello, hello. Hey, Zoom, whoever is online, can you guys hear me?
Hello, 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 hello.
They're still saying no. Hey, can you hear me now? Everybody online? Can one more person confirm? Awesome. Yeah, I'm speaking a bit low. Cool. I'll start again. Hello, everybody. Okay, I'm Shivam. I work at Swiggy, and I've been working there for the past 1.5 years. I work on homepage level recommendation systems, where I and one more person, both of us, we build models to show restaurants to every user, and that's at a personalized level, right? And similarly, my team, like part of my team, works on menu recommendation, where we recommend items. So there's a recommended section, and that's where all the things happen. And yeah, so yesterday Surinder covered. Okay, before that, one more thing. So since this is an industry track, we call each other by name. So please don't call me sir, just call me Shivam. It's okay. Even after the session, it's fine, right? Yeah, cool. So yesterday, Surinder covered the parts of the data science process which come before deployment. Like product manager will come to you with a problem statement. You as a data scientist will work through the solution. You will see whether data is available or not. You will see what the formulation is. You will see how feasible it is according to the given engineering constraints, and you will build the solution. Now, what I'm going to cover is deployment and what happens after deployment, because for a data scientist, work doesn't end there, right at the model building. So yeah, so these are the topics that I'm going to cover. Like first, I'm going to discuss general development process, how it is different from an SD process and where it differs exactly in data science. Then I'll come to model deployment and various parts of model deployment, what kinds of models we can deploy, how we are going to discuss like the feasibility of it, and then which mode of deployment you're going to choose. Then we do experimentation. This is not offline, this is largely online experimentation, which is after deployment that we do. Then now you've deployed it, you have done A/B testing. Now comes the part, like the crucial part, because your model is not always going to remain good. So we are going to do two kinds of monitoring. One is model monitoring and one is data monitoring, based on which we'll have continuous training pipelines, which keeps our model fresh. And then so as a data scientist, you will build models, but it's not always necessary that your model is the endpoint, like the end of the pipeline. There is almost always a business layer on top of it as well, which basically caters to various business rules. I'll come to the business rules, which like using case studies, what kind of business rules there can be. And then I talk about abstractions, which basically apply to the whole process, not just deployment, post deployment, like the whole process of data science, and how you can basically optimize your basically the whole pipeline. Cool. So development process. So first is, this is the simple software engineering workflow where you start coding, and then you write unit tests and all the tests, then you deploy it, and then you monitor it. For monitoring, you have some metrics, traffic alerts, and your code alerts and all of that. And then either you have bug fixes, either you have figured out something, or you have new changes, you go back to code, and this loop continues. And this is a very deterministic kind of process, because you know what your code does, what goes as input, and what comes out as input. And so it's very easy to monitor general software development pipelines. Coming to data science, the whole process becomes like this. So you still have code, but apart from code, there are more other things. You have parameters which you have to tune, being a data scientist. There are multiple data runs depending on how your data is, how you have done your sampling and all of that. And then you will do model runs. This is the offline experimentation part. You will find the best version, and then you will deploy it. Before deployment, you'll have some metrics, business and tech metrics, and then you'll deploy it. And deployment, so A/B testing is also part of deployment only. After, when you'll do A/B testing, and if it works, if it's successful, then you will deploy it at like pan India, or like whatever your service is, and then you'll start monitoring it. Based on what you get, you're going back to your data and parameters and model runs and code to get a new version, and this cycle continues. Now here, things are not deterministic, right? Because your data changes with time, your model changes with time, your whole relationship between data input and output changes with time. So even if everything is running fine, your data itself may degrade with time. So you need to have monitoring practices like in between the whole, like in all of these parts of the pipeline, so that you can detect early, so that you are proactive in determining the degrade, and quickly handle the issues, rather than someone coming to you saying that, dude, your model is not working for us, what do we do, right? So, and yeah, and general difference between software engineering and data science is this, like monitoring is part of it, but yes, there are a few extra elements that data science has, which is data and pipeline, CT pipeline. CT is continuous training, CI/CD is continuous integration and continuous deployment, which basically means that you make changes in code and then you run all the tests. You keep running it daily just to see whatever changes you're making to the code are working fine or not. And then you do the continuous deployment, because in software engineering, you can almost always automate this deployment process. In data science, there is an extra step, like you do CI/CD, but you also do continuous training because you need to refresh your models and then you do model survey. And of course, this is conditional on what kind of model you have. For example, our recommendation systems are something that everybody is exposed to coming on the homepage. So we have to be careful what we are deploying, even through this automatic continuous training pipeline. So we have to do A/B tests every time, whether something is not ruining things, right? So it depends on what business problem for which team you're solving. Yeah, like this is just what I say. So this was the basic thing, like the whole process, what parts of which Surinder covered yesterday. Now we are going to start with different specific things which Surinder may have just skipped. Cool. So first is we discuss model dichotomy. So there are two kinds of models that we usually have to work with. One is online, one is offline. Online, here I mean you deploy something, let's say your gradient boosted machines or even neural network. All the inferencing is happening online, like model is deployed, you are sending inputs right there, it is computing all the gradients and everything forward pass and coming up with the output, right? And then we return that output. So that is online inferencing. Offline, what happens in offline? We do batch inferencing, but in an offline manner. For example, I'll assume that a night before, this is what I'm going to compute. I'll come to the use case where all of these come, like where online makes sense, where offline makes sense. But so in offline, we do batch inferencing. We take, let's say, last 1 day of data and see whoever was active and then generate inferencing for them and then serve the results next day from a low latency data store so that we can quickly get the recommendations or anything out, right? I'll come to the exact use case in a bit. So online, like I said, right, you inference real time. All the compute happens in real time. So you call the model, you get the predictions, and they are available immediately. They are used immediately by the end system, whether it be another ML model or another engineering system or anything, right? And the artifact that is deployed here is the final model. Like it can be pickle, it can be anything, but you deploy the final model and it will be just loaded in the memory and then in like normal Python code, right? You send some inputs, you get some output. Offline models. So like I said, it's offline batch inferencing. Everything, all compute, whatever you're doing, whatever assumptions you're making, whatever feature engineering you're doing, everything happens offline. And predictions are available, but they take time to propagate in the final system so that they can be served. And usually it's done at a time where there is like that delay, like we are fine with that delay. For example, recommendation systems, right? Preferences do not change, as in I'm not talking about TikTok like services where preferences change in an hour, but something like Swiggy where preferences don't change in like a day. So we can take a leeway that will generate predictions for a day before, and then serve them next day. Here the artifact is not a model, like you already have a model deployed which you have trained, which you have stored offline, but the artifact that you deploy here is a Spark job, which is basically doing all the heavy lifting. It is taking all the data from the databases, creating a final table, adding features to it, and then loading the model, doing the inferencing, and then saving those scores to any data store. I'll come to that later. So this is something, if you guys have any question, this is before this is to make this interactive. I'm going to ask you, what do you think should these models be, online or offline? So before this, if you have any questions about online, offline, anything you guys are not clear on, I'd be happy to answer them. Um, is it we can discuss that later, but is it relevant to this thing? Cool. Does
Hello. My question was, if there is a offline batch and you
Mhm.
have processed and made the prediction,
Mhm.
simultaneously there is, let's say, a case where you thought there is a delay, but the customer changes mind for the recommendation system online. You
Mhm.
see, then how do you tackle that? Because offline you had some predictions,
Mhm. Mhm.
and suddenly out of the blue there is some offer, say they got some cashbacks.
Mhm.
So the traffic will be diverted to that case.
Uh-huh.
S- So in that, what is prioritized, offline or online?
So that depends on business objectives. Usually there are various entry points. For the offer entry points, there would be a, like for example, separate widget where people would go and order. And recommendations. So recommendation is largely what they are there to help you discover, right? To show you similar restaurants that you have ordered from, but new, nothing like it can repeat as well, but also new, right? So it's meant for discovery. So that's where what Surendra was talking about yesterday, explore, exploit dilemma comes in. So recommendation systems, like everybody understand that this is what they are used for, and this coupon related or offers related things, they come in a separate like entry point. Either there'll be notification, there'll be a separate widget, those kind of things.
So no, my main question was, if there is a conflict between the online and offline, what
Hmm.
will be prioritized?
So see, for that there needs to be an online model as well, right? So that's what the feasibility part comes in, that when you have deployed an offline model, you're aware that this is this is an issue that needs to be solved, right? So there are multiple solutions. If it first is, it's very hard to determine in recommendation systems what the intent of user is. Like, you came on the app, I don't know what you're looking for. I may predict it, but that might be wrong, right? Recommendations, just like you're saying, I've generated some recommendations. It's not necessary that those recommendations are what you want, but that's the nature of recommendation. Like, I never get 100% label, because most of the times customers also don't know what they want. Like, they come on the platform, they see what works for them, and then they order. Sometimes they just randomly experiment. So even like, it's very hard to detect what you might want. But even if it's something that like we can detect in a sort of offline manner. For example, I showed you something, and then you did not use that at all. Like, whatever I showed you, did not order from that list, you ordered from somewhere else. That's a signal for me that whatever recommendations I showed to you were not relevant to you. So we handle it in an offline manner rather than online. So real time, it's, you have to have various infra in place to handle this kind of things.
Thank you.
Mhm.
But the situation is, when the user has given you feedback enough on your recommendations for the last, when you showed it for last couple of times or last n times, that he or she is not interested. That phenomenon is called impression discounting. So your long-term interest might be saying something, but your online behavior of recent says something else. So you can discount that. I mean, you can look at the recent behavior and start discounting the long-term interest that you, or the recommendation score that you have. They work in sequence. So one is offline, you have generated the score, the user's affinity towards a particular product or a category. And when you start showing it online, because the offline behavior, it will take some time to decay out. So if you want to react very fast to it, there is a corresponding online component, like you were saying. Online component will start discounting or taking care of these differences.
Does anybody have any questions about online offline? Cool, then let's discuss the first application. So fraud detection, I'll give you some context. So at Swiggy, there are various frauds from both customer and delivery executive perspective. Uh, and these are some novel techniques which you wouldn't guess how they're making, like doing these frauds. But customers will, maybe they order something, then they cancel, they find out some loop in payment gateway, and then they will ask for a refund. They'll get a refund, they'll also get the order. So there are multiple kinds of frauds that happen. So this is the context. Now, from this context, what do you guys think would the model type be, online or offline? Mm-hmm.
So I'm saying that I think in my perspective, it has to be online
Mhm.
because you're saying that there are novel methods in which the fraudsters or the scamsters work, which basically means that offline models cannot be trained for all of them, but online models, because they have real-time inferencing,
Mhm.
it's much easier to detect fraud because there's no delay in the data given and the output received.
That is one. Plus, novelty is there. Plus, what happens is you do not want a delay, right? You cannot assume something that this is going to be a fraud next day. You don't even know who to run it for. Like next day, whoever is going to make a claim, like there will be specific situation for which you will run this model, and then you will see whether your model said this customer or this delivery partner was a fraud. Like how confident are you in calling this person a fraud? That's when this will be kicked in. So yes, this is online. At least that is how it is at Swiggy. There could be other use cases as well where in situations it is not required to be online, right? ETA prediction. ETA is, of course, everybody knows, right? You order something, we predict what the time of delivery is going to be. What do you think is it going to be, online or offline?
So, of course, online would be much better because you'd know the real-time traffic updates.
Mhm.
But for example, if for the past 7 weeks on a Sunday evening at 7 p.m. in Ahmedabad, there's been a high amount of traffic on a certain road, then it's extremely likely that on the 8th weekend as well, there'd be traffic on the same road as well.
Mhm.
Similar amount of traffic
Mhm.
as well.
Mhm.
So although it can be done online, offline should also work in this regard, is what I feel.
Okay. So yeah, and you're correct. We like it should be online usually, right? But we can do it offline. But offline will come with some caveats, like because you're making a lot of assumptions, right? And what happens is when you have a customer-facing product, you have to also think of customer experience. Like let's say you said that based on previous traffic, it's going to be delivered in 30 minutes, let's say, but it is actually more traffic due to some reason or the other. Maybe it's some seasonality, right? Something is there, and then it turns out that the order that is being delivered is in 35 minutes or 40 minutes. Now that's a very bad customer experience because we have told that customer that it's going to be delivered in 30 minutes, but we are delivering it in 40 minutes, right? So from that perspective, we have to make a either trade-off, like what part of it are we going to compute offline, what part of it are we going to compute online, or whether it's going to be 100% online. Or then traffic also comes, like if it is something that we can sort of take on as an org, if it's not too cost prohibitive, then maybe online makes sense, right? Like maybe compute is like so when you're computing offline, you have to make a lot of assumptions, as in for whom are you going to compute, right? From point A to point B, what distance, what ET are you going to calculate? You don't have that information a priori, right? You have to have some assumptions. So when those assumptions come, that's when coverage issues start coming. You've assumed this, that user is going to be in this area, and from this area, this is the distance to this particular restaurant. What happens if this user moves? You don't have any compute for this guy, right? Then you have to recompute it. So in offline, this coverage issue comes. I'll come to that when offline and online are there, and what extra efforts you need to put in when offline is there, right? But yes, here, okay. Third thing, distance prediction. I'll give some context. Of course, distance is just predicting distance between point A and B, but depends on where it's going to be used. So since ETA is going to be calculated over distance, let's say we are using this distance prediction model inside ETA prediction model. So what would it be, online or offline?
Maybe offline.
Sorry,
Offline,
can you expand on it? Why do you think it would be offline?
generally, the distance between points does not change, right?
Mhm.
It just remains constant. So we can deploy offline and use that information in predicting ETA online. So as you said, that the component of ETA may be online and offline. So this distance prediction can be offline.
Okay. You are correct, but again, in a lot of situations, it would be online. I'll give you some examples. So one is yes, because distance is largely going to remain same. Yes, it's going to remain offline. But what happens is, again, you have to take some assumptions, right? If you're calculating it offline, you have to calculate it for all the pairs. So there you have to take some assumptions that what's the granularity going to consider, what are the major points you're going to consider, how are you so going to solve this novelty problem as in distance between 2 points. Customer can be at any lat long, right? So you have to calculate distance from there. Plus maps change, new routes come, old routes get blocked, or like whatever, they get closed. There are multiple ways in which maps keeps on updating, and there might be a small, there might be a change which is leading to a smaller ETA, which delivery partner knows, but we don't. So distance can be used in a lot of ways, right? Distance could be an input to ETA, which I said, but distance could, for example, at Swiggy, distance is also used. How much are we going to pay the delivery partner? Because however, like we have to pay him for the fuel and all the time. So the distance travel, now let's say we have predicted the distance is 20 kilometers, but there's a shortcut which makes it 15 kilometers. We are paying for extra 5 kilometers, and it's an extra bleed, like burn for Swiggy, right? So ideally, as a data scientist, you would be asked for these side metrics as well to see if you can like if they are big enough, right? So multiple things come, so it can be offline as well as online, but mostly yes, offline makes sense because distance is largely not going to change. Cool. What about recommendation engines? This I've already covered, so this should be easy to answer. Anybody? Come on, guys.
Would it be both, like a hybridized mix of both
Exactly.
online and offline?
It can be both, as in hybrid. It can be just offline plus some fallback. Sorry, offline plus fallback, or just online, right? So you take real-time inputs and do something, and then you have some. So it can be both. Again, if you are using, like if you are going with some hybrid model, then you have to be careful of how the cost is going to be, as in because you will be having storage cost, compute cost, as well as real-time compute cost. So you have to have a trade-off between what you're going to keep, what you're not going to keep, because they add on, right? And for example, at Swiggy level, we have a lot of traffic right on homepage, and if this recommendation model is just running for every customer every day, like I know daily around 1.5 million customers come on the app. Now this model is going to be run for all of the customers throughout the day, right? So there is going to be a huge traffic, so we have to be cognizant of what the trade-offs are going to be, storage versus online.
So I've got another question with the distance prediction. Can it be hybridized in the sense that, for example, if I use Swiggy and I order 10 times a month, right? Out of those 10 times, 8 times a month, I'm either going to order at my university or at my workplace or at my house. So once Swiggy has got that down, can then the distance prediction, that part of it, be turned to offline? And then, once a month or once in every 3 months or once in a specified large amount of days, there's an audit in which it goes back up online again. It cross references versus Apple Maps or Google Maps, and it checks out whether there's a faster route between a restaurant and a location. So distance prediction, as in the location of the, because of course the location of the restaurants has to be offline, is what I'm assuming here,
It's going to remain constant.
right? So because now that you have offline both the location of my workplace as well as the location of the restaurant that are around my workplace or are serviceable to my workplace. So can then the distance prediction for my case be converted to offline? Therefore, you require lesser online processing capacity.
Depends how many other customers are there like you. So if I can sort of cluster one set of customers into this who have a set of locations from where they order from, like they don't roam around, they don't order from anywhere else, like let's say few set of locations are there, I can compute it. Or I can take an assumption that yes, I take all the customers and their saved addresses, just the saved addresses, and calculate the distance. The problem comes here is how many restaurants am I going to consider to calculate distance for, right? It can be any radius, 10 kilometers, 20 kilometers, 30 kilometers, and it can be anything. I have to iterate through all of them. So that takes a huge compute. Like there is a possibility that, for example, in dense areas like Bangalore, Delhi, Gurgaon, all of this, there are a lot of customers, let's say 50, 60 or 1 lakh customers. For each customer, let's say there are two, 3 addresses on an average saved, right? And in that city, there are, sorry, I'm talking about customers. So 40, 50,000 restaurants. Then for each customer, there would be what, 1 million customers, and 1 million customer may have around 2, 3 saved addresses. So you multiply this itself becomes huge, right? And then, so we say storage is cheap. It really is not cheap because you have to store it in a multiple ways to serve it finally at the end. So you have to store it in a low latency network so that you can quickly go to that key value store sort of database. You enter that key that I want distance for this customer comma restaurant there and get the distance out. So that itself is a huge storage space and an extra cost. So all of that you have to take a trade-off. So when Surendra was talking about feasibility, that's when it all comes in, like whether it's going to be offline or whether it's going to be online, like what the network throughput is going to be, how much traffic are you going to receive, all of that. So it can be, but depends how feasible it is.
Sir, is Swiggy plugged into Google Maps at some level, as in to get the addresses or to
Yeah,
get the
yeah.
distances?
It uses
So,
Google Maps.
Right. I'm not sure whether this exists in India right now, but where I study in Glasgow in the UK, what we can do is we can download maps of the entire city, which like an offline
On
map
Google
of
Maps,
the
right?
entire city, and it has like not a lot of information, but some level of information about what the traffic patterns are usually like. So it just like although the route shows that it's like the roads are empty, it comes with a caution that this road or this between these blocks there might be some traffic between these and these times. So can that technology be applied here to convert the entire thing to offline with a like I'm just trying to decrease the amount of online processing because online processing is much more costlier than storage, right?
Yeah. Okay. So depends how this data is available. First, Google, like whatever offline maps you're talking about, that are only available in Google Maps, right? In the app. So we use Google Maps API to get all of this, but Google Maps API itself is very costly, right? So we went on a tangent. We already have all the ping data from delivery partners. Can we have sort of our own offline maps? So there's an alternative map called OpenStreetMaps, which are open source, just like Wikipedia. People go and contribute on them, and there's a peer reviewed process where they decide whether this road is going to be there or not, and then they decide that yes, this is the final road. So we use that at a lot of places. Now that kind of maps we have to augment with all this traffic related details, right? Google has data coming from everybody, like all the Android devices basically. We have data coming in only from delivery partners. So using this information itself is not that easy, and even if Google is making it available, it will, like, this data itself would be very costly. So trade-off may come like that, it's not worth it, right, rather than comparing it online.
That many a times I have seen that oh, while delivering the food or getting, oh, let's say cab or something,
Hmm.
we do not have proper walkways. So
Proper.
walkways or something crossing.
Hmm.
So it is just like I have to just cross the road to catch any or get some food, but the delivery guy has to come around 1.2 kilometers or 3 kilometers long distance. So is there any way that it is we can optimize like walk-in or
Depends if it's legal to do that, like walk from like across the road. You can do it as a right, as a human, like just walking around, right? A vehicle can do that or not, I'm not sure. Malab, if it is possible.
No. I am asking that delivery partner should, like in the app, can it be introduced like walking option that given to the user that if this is this, you will get the delivery 5 minutes early or something like that.
It can be done. I don't know how many orders are there going to be, because customers are usually very determined to get it at their homes, like just right at the door.
Usually in the office, they have to come down to the security guard.
That's like they have to, because it's a requirement from the like office, right? Like they can't get it delivered to their door. I don't know how many customers will actually be willing to walk, but yeah, this could be done. The bigger problem here would be that DE needs to ping the customer that I'm here, can you walk till this place? Well, there has to be some incentive. People don't do anything without incentive. Any other questions? Cool. So now we'll come to the steps of what deployment means in terms of online model. It's just easy. Like you create your final binary trained model, and then you put it somewhere, and then you register your model in a model registry. Model registry is just an index of models where once you put the model there, it creates an endpoint to hit, right? Just like an API endpoint, anything, fast API, Flask, whatever. And then so that's what module registry does. You register it, and it creates an API endpoint which you can call through anywhere, anything. Yeah, that's just like it's simple. That's why online models are easy, but they're compute heavy. Coming to offline. Now, since you're not deploying a model in offline, you're deploying a Spark job. You will first write the Spark job, which will basically do everything. It will prepare population. It will get the feature data from feature store. I'll come to this in a bit, what a feature store is. Then add features to the population, do the inferencing, like after loading the training data, and then push this data, like these scores, to some low latency storage. Low latency could be storage, Redis, where you store at various keys. For example, I'm generating recommendations for customer. My key would be customer ID, and I'm storing scores for all the restaurant which are nearby this customer. So I'll store a list of, maybe like it can be any data structure. We have to see what is going to be more efficient, but it can be like list of restaurants, score pupils, right? And then you put it in a key value store similar to Redis, and then in the endpoint, you basically integrate just like you integrate with MySQL, you integrate it with Redis, where given the key customer ID, you just get this data out and serve it to the final layer, right? And just like I said, like model endpoint is basically reading from key value store, so it becomes very efficient. So there is no or minimal compute happening in the model. Everything has happened offline. Now, like I discussed during the use cases, there are problems with offline. With online, you will not face this, but largely with online, offline, you have coverage issues because you have made some assumptions. It is not possible to store recommendations or store any scores for all the use cases that may come on the app, because you don't know where the user is going to be, what the context of the user is going to be. So there has to be some fallback model, which is basically going to pitch in when this model is not working. Now that can be another hybrid model, like he was saying, there can be another online model, right? When you have not when you do not have any scores, or it can also be like where you have some popularity based model where you know what is the popularity of, for example, in Swiggy context, restaurants in this area, and for this customer, maybe this is his inclination towards popularity, and that's how popularity scores are going to be there. Or cold start problem where you have new users or new restaurants, how are you going to recommend for that? You will need, like, since offline models will not be good there, you will need to have a fallback model in that case. And these models are usually simple, like except cold start problem is a separate problem in itself, but these are very simple in implementation. They also function as a fallback in when something fails, like your offline models, even your online model can fail. So there needs to be something which comes as a fallback, so that you gracefully degrade rather than just degrading like in a worse manner, right? So at Swiggy, there are, for example, two fallbacks. One is you have offline model, then if offline model is not working, you have popularity based model. If popularity is also not working, then a random model, like which will just randomize the list so that it never fails. User will see something. It's not like user is not seeing anything. It may be a degraded experience, but it will be something rather than nothing. So that's where fallback models come. So now this is the last part where how deployment happens. There is canary, automated, then shadow. What canary is, you deploy it basically in a phased manner. So let's say you have created your model, you have finalized that this is the model that I'm going to use. You deploy it city by city. For example, I'll first deploy it in tier 3 cities where traffic is very low. I'll see how it's doing. Then tier 2 cities, then tier 1 cities. So as you come towards tier 1, a lot of traffic starts increasing because majority of the customers are there and those are the dense areas. So that's what canary deployment does, right? It depends from org to org how you're doing it, or from use case to use case how critical the model is. Similarly, then automated deployments come when you have like now you have determined the cycle that it should be done in phase or whatever directly, but you have to keep refreshing model, right, after some time because distribution changes. So automated deployment comes when you have those pipelines created and it deploys automatically. So that's the second mode of deployment. Then comes shadow deployment. Now shadow deployment is, so you have model A and you have model B. Model A is already deployed and it's running. Now you want to see how model B is going to do, right? Because this is the new replacement for model A. So for that you do shadow deployment, where you basically send the same traffic that you're getting to the original model and you send it to the shadow model. So shadow model will generate recommendations, but they'll not be shown to anybody. What it will give you is it generating the right responses at the right time? And if the model is like ETA prediction, then you directly get the inference there and you see like you can directly get the feedback on your model. And if it works with the production model, then yes, you can directly deploy it, right? Then A/B testing sort of things are not required. So yeah, this is the deployment part. That's where deployment ends. Does anybody have any questions about deployment? Yeah.
Particular to deployment.
Mhm.
But while you were talking about the fallback models, I just had a question. So in essence, yesterday, sir was also talking about user features. So does the recommendation model involve those user features? For example, I'll give you my example. I'm vegetarian, right? And all the food that I order from Swiggy is of 2 or 3 particular types. So I generally order like sandwiches, burgers, and or fries.
Hmm.
And my order ranges around that and that only.
Hmm.
So the next time that I'm looking for food on Swiggy and I'm at a different location,
Hmm.
will your recommendation system say that, all right, this guy is a vegetarian and this is the kind of stuff that he likes? So will the recommendation system display that kind of food, or will it display the popular kind of food, or the kind of food that's recommended, or how else would it recommend food?
It should. That's the ideal scenario, right? But then it comes to that fallback, trade-off thing. If I'm computing it offline, I know you've only remained at these two places. I'll generate recommendations for those. But you've gone to some third place. I will not have some offline recommendations for that, right? Now the situation comes whether I have an online model or not. If I have an online model, of course, since the model itself will learn your preferences, it will start showing you relevant things. But if online model is not in place, then we will be using some fallback model. Now fallback models are supposed to be simple, like they're not very complex in logic. It can be simple popularity, it can be simple logistic regression, it can be anything, but it is very easy, so that it's just not receiving a lot of traffic and it can handle latency, like if first model falls, right? So depends on the scenario. If we have offline scores computed for you, then yes, they should have what you're looking for. If they don't, then either popularity is doing its work or the model itself is wrong, like model is not capturing your preferences. And yes, so this is the kind of user features that should be taken in your recommendation models, but depends how you formulate your problem, right? It can be simple collab filtering, or it can be some GBDT based or neural based recommendation engine. So then dense features and all will come, where Surendra was talking about it yesterday, right? Cool. Any deployment related questions? Anything? Cool. Online experimentation. So by experimentation here, I mean once we have deployed the model, we want to see how good it is performing. Like you have seen, it is working well in offline, but when it is deployed online, there are a lot of factors at play, not just your model, not just your environment. So you have to see how it is performing online, and that's when you do online experimentation. So this is what I talk about, like uh, why do we need online, right? In offline, first there are many use cases where training data itself is biased. For example, in recommendations, so there was a last model running in recommendation. Feedback is usually depends on your objective. For example, if the objective is probability of conversion, like what is the probability of a user ordering from a given restaurant, right? That's the probability that, let's say, model is going to predict. Now what I'll be doing is I'll be taking historical data where I'll be reading all the orders which the user made, and then based on that I'll try to predict, right? But the problem with this is your data is biased in terms of your last model itself was showing some end results out of which the user ordered. There might be situations where out of these 10, like in the remaining 10, remaining 20 or outside which are not in this 10, there are more relevant restaurants, but we never showed it to the customer, right? And that means customer will never order from it unless he or she is searching for it and then ordering, right? So data itself is biased, and if data is biased, you're going to evaluate it offline using some NDCG or AUC or whatever, like some metric. That metric will also be biased. So even though your model might be beating it offline, it is not possible. It is not always necessary that it's going to beat the current model in online fashion, right? In metrics. Then there are also, so you have just your model in terms of technical metrics, as in how the AUC is going to AUC ROC is going to work or improve, or NDCG is going to improve, or accuracy is going to improve, right? But when it comes to online, we also look at whether this model impacts other business metrics as well or not. For example, there could be a metric that I want to show nearby restaurants nearer, like because it is a better customer experience. Otherwise, they'll say that they're just showing me the far away restaurants, right? Those kind of things, like we see how much, like in online experiments, we see how much it's going to impact in that direction, and then we decide whether we should deploy this model or not. So it's not always necessary that whatever you create offline should be deployed online because it might have some adverse effects on other business metrics, which could be revenue as well, right? So yeah, why online? Yes, shadow testing I've covered, right? You see, you deploy it along with your model, and then you send it the same traffic as you are sending to the, like, as the first model is receiving, and then you see how it's performing. So there you check the performance of the endpoint, whether the endpoint is performing well or not, whether it can scale up to the traffic or not, and you see how the model is doing. For example, like I can't do this for recommendation because I don't have feedback for my new model, but for ETA prediction like models, we can do this. We can check how they are performing uh, as a shadow. So the main question we are trying to answer is, can we replace the new model, sorry, old model? Oh, I've written this wrong. Okay. Can we replace the old model with the new one? That's what we're trying to answer in shadow. So now come A/B testing. How many of you guys are aware of A/B testing? Cool. Okay. I'll maybe then I'll just explain it intuitively. So let's say you have two variants, option A and option B, A/B variant, so A and B, where A is control, which is your current model in production or current variant, and then option B is something that you want to see how good it is, right? It can be anything. So you have these two variants. You want to see how good the B option performs when compared to A. So you do A/B testing. What A/B testing does is you take some cohort, some random visitors, let's say some X traffic, 5%, 10 traffic of your whole like pan India. Like you can also decide whether it's going to pan India or some city or something. So you select 5% of population, for example, and then you divide them 50-50. 50 for option A, 50 for option B. And then for each A/B test, you usually have a success criteria that this is going to improve my relevance, that this is going to improve my revenue, that this is going to reduce my average perception of last mile distance, delivery distance, right? So based on that success criteria, you decide which was the winner. For example, in this diagram, option A had 17%. It could be anything. Let's take it conversion. Like option A had 17% conversion and option B had 25% conversion. So you have seen directionally it works, but to have a sure shot answer whether it works or not, or whether option B is really performing well, whether it's not some random effect, right? Could also be random because you're doing random sampling. You do hypothesis testing. So I think Professor Anirban also talked about it, like how to do hypothesis testing. So we have two samples. We'll do hypothesis test and see whether this difference of 0.17 and 0.25 is statistically significant or not. If it is, then we conclude that our experiment was successful and option B is a winner variant, and then we go ahead and deploy it, like finally like roll it out to basically the whole 100% population rather than just 5. So that's the A/B testing in at a glance. If anybody, so now this is round 2, basically for the same 4 application, we'll discuss what makes more sense, shadow or A/B. But before that, are there any questions related to A/B or shadow? Anything related to online experimentations, anything? Cool then. Same applications, fraud detection, I've already given the context. What do you guys think? Should it be a shadow or A/B? Shadow? Why? Mm-hmm. So Abhi, we are comparing two models, right? So model A and model B. I have a new fraud detection model. So for that model, does shadow make more sense or A/B?
There are two models, then
Well, one is already there in production, right? Like I'm already using it to detect whether somebody is fraudulent or not, and then making decisions based on that.
If it is in the production that which it is tested and it is fine, so I believe we should go with shadow.
Okay.
Then if the shadow is outperforming the first,
Hmm.
then we can replace it. Otherwise, whatever it is, suppose A and B.
Hmm.
So A is the earlier one and B is the latest.
Hmm.
If B is surpassing A, you can replace it. Otherwise, you can keep it A and
Okay. Okay.
parallel.
Cool. Anyone and any other? Okay. So it is shadow. For example, at Swiggy, it is shadow, but it again depends on use case. For our use case, it makes sense to have in a shadow mode. But for example, Surinder, who was talking about it yesterday, at Flipkart, it's in a AB mode because use case is different there, right? You're trying to predict whether a customer who has ordered something from Flipkart is going to return it back or not. So there are multiple fraud cases there. So, and it's a very big problem. So there they do it in an AB fashion where they prevent the user from like they make the user let the user complete the transaction, but they don't let the user do it on a cash on delivery mode, because that's where the frauds happen. Like you take the order and then you don't pay or whatever, right?
My question is a little bit pertaining to profitability or feasibility of selection of certain models.
Mhm.
For example, you have a model in place for fraud detection, for example,
Okay.
and it is 16 point, it's 87% effective. So
Okay.
13% of all frauds are undetected.
Hmm.
Then there's another model that you have that is that will probably be 87.8% effective.
0.8 delta.
Yeah, 0.8 increase.
Hmm.
But to apply that to, pick that fraud detection model up and take it out and put in the new and 0.8% better model,
Hmm.
it's going to cost you a large sum of money.
Hmm.
So how long do you look at the profitability of the current model that you're applying to ensure that it actually makes sense financially? Because if the profitability coming from that 0.8% rise is 1 crore rupees over 10, 20 years, and it's going to take you 5 crore to apply it, might as well not apply it, right?
Exactly. Yes.
So what time frame are you looking at? Because in 5 years it might be 2 lakh, but in 10 years it might then go up to 4 lakh, right?
So it is how I have seen it happen is it's not really time frame. They look at the trade-offs. So right now I'm seeing 87% accuracy is saving me this much money, and 0.8 is going to save me this much extra, as opposed to how much is going to cost me in deployment, right? If there is like a very big difference between these two numbers, then it makes no sense to even deploy it now. Like you can't just go and deploy like very big, huge models, very complex models, which are only giving you that simple, very small gain, right? Just like he was talking about formulation. Like currently people think about directly deploying things as neural network, whereas you should start from the basics, because a lot of times 80% of the work, 80% of the gains you can receive from a very simple model. Like from 80 to 100, of course it's going to take time, and there might be a scenario where even to reach 90% it's going to be like exorbitant, right? But if business can't support it with that 0.8 gain, then it makes no sense to apply it, like even from the current time frame. So then your next way of solving it could be, where is it that your model is performing well, and how can we incorporate those features or those trends in the current model, so that it's like we're using the goodness of that model. Or it can be like, if an offline way is possible, then use it offline, right? Then that compute you will just put it offline, and offline jobs can be optimized. So yeah, that's the trade-off. Like, mm-hmm. No, shadow is strictly that you have deployed one model. Like it can be a third model, okay? And there is one model, model 1, model 2, and you created third from 1 and 2. So model 1 is already in deployment. 2 you found to work well in offline. Now you want to test the third, which is a combination of 1 and 2. For third, you can do a shadow, right? You can, this is already deployed. Whatever traffic is coming to 1 will also be sent to third, and you'll see from the feedback how it is doing and all of that. So that is shadow. Like shadow is not like you create an ensemble and do something. For shadow, it's just model A and model B. Like model B could be anything. Cool. ETA prediction, shadow or AB? Why? Mhm. Mm. 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 I don't understand. Why should it be shadow then? Why should it be in a shadow mode? Like why can't it be AB where you're distributing traffic to two different models, like both the models, as opposed to you're sending all the traffic to model A and B is just running in a shadow mode. No one is able to see, like no customer is seeing what it is predicting. So why should it be shadow? Hmm, hmm, hmm. Hmm. That's the difference I was trying to come at. Like shadow, like whatever traffic you're sending to the shadow model, like model B, whatever output it is sending, that is not being used by anyone. That is just being logged. So that's what shadow testing is. Like, uh, okay. So this is model A. This is model B. This is app, right? So model A is being used on app. Now customer comes, who is coming on the app. So whatever traffic comes to A, model A, is sent to the app to be shown, right? But whatever comes to this traffic is also sent to B, but this does not go to the app. This goes to some log. So it does not contribute to anything on the app. Like that's what shadow mode is, because you're running it in a shadow. Sorry, orders meaning? Hmm. 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 Could be, yes. Well, there can be n number of problems. So that inconsistency would be there. Hmm. Mhm. To some extent, all three of you are correct. What happens is, so answer is shadow plus AB, right? So shadow hoga, like you will do shadow, but that is because it's cheap. AB mein what you have to do is, so in AB there is app again, there is A, there is B, and there is 5% traffic here, 5% traffic here. So you're taking a chance on B without even knowing how it's going to perform, right? In shadow, you can cheaply do that by just logging it. So there will not be any impact on the customer. So you can quickly decide whether A or B works well or not in a shadow mode, and then do an A/B. Like you should always do an A/B to see how it has impacts on other business metrics. Like here you've only checked how it is doing in terms of ETA, right? Let's say model A said 32 minutes, model B said 35 minutes, and model was delivered in 34 minutes. So B is better, right? So you've checked that, but you have not checked how it's going to improve your like overall business metrics. It's possible it might have other impacts, or maybe because of it, because now perceived time is less and ETA is used throughout the app, like on each customer card you see, right? Okay, how many minutes it's going to deliver. So customer sees that, and based on that they make that decision. So it is possible that because of model B, conversions are also improving. So you would want to know that impact as well, right? So AB is always suggested, but shadow is a cheap way to find out which model is working better. Distance prediction. It's not. Mm-hmm. Mm. Uh, yeah, like to some extent yes, but largely so distance, now you have to consider how distance is being used, right? One is it can be input to a ETA prediction model, or it can also be a input to for example, it can also be a perception thing. For example, on homepage we show that there are 1,000 restaurants available near you, right? And at places, so previously we used to have very less distance radius, so we used to show around 200 restaurants, whereas on Zomato there used to be larger number of restaurants. So people used to compare that Swiggy does not have a lot of collection of restaurants, even though we used to have, right? So it is also perception problem. So distance is used there, and if I have improved my model, which is calculating better distances, and in terms of that I'm improving that UX, then that should be used as AB. Otherwise, of course, shadow works, and you might not even need shadow if it's an indirect input to ETA prediction model, right? But if it's something that is directly being used, then AB makes much more sense, because it may have unintended effect which you're not aware of, or which you just want to measure, right? Recommendations. Can you give me the mic?
In terms of ETA and distance prediction, how you are controlling the variability at the service providers, in your case, restaurants
Mhm.
and the delivery agents.
Mhm.
So how you are controlling the variability in terms of in your models? Variability in terms of, for example, uh, how you are ensure that in this particular time the restaurant will prepare the order and they will give for sure.
Just based on past data,
Okay.
like that's what ML models do, right? You look at historical data and you see, like, so there are multiple components: food preparation time, then delivery agent's location till restaurant's location, how much time that is going to take, then from restaurant to customer's location, how much time that is going to take. So it's a combination of multiple smaller problems, right? Subset of the problems. So you predict all of them and then you take a something like that.
Okay, and in terms of delivery agent, you will see the past delivery driving behavior of the individual also. Uh, how much time they will take to cover this much of distance, and then
Technically
and-
you could, but I don't think we do as of now,
okay,
because that is very hard to characterize, right? Like
yes, because it's a individual means the way they how much kilometer means that KPL not KPL. How much kilometer they cover in a particular time, that's vary from individual to individual. I just want to know whether this part is there in your model and
I don't think so. So I don't particularly belong to those teams, right? So I don't exactly know the details of models. This is the part I was aware of because of knowledge sharing sessions, and like they shared this. I don't think they are taking this part, like how the DE drives into account, because what happens is there's a very, like, even if you train for DE behavior, like this particular DE drives this way, what happens is D churn is very high. So almost every month, like some X, and X is a very big percentage, like X percentage of Ds are replaced by newer Ds. So even if you train your model to take this person's preferences into account, it's possible that next month this person might not be there. So you have to have some novel ways of solving that.
okay, I asked this question because yeah, these digital platforms are trying to improve the efficiency with gradually they are moving towards a more efficient systems.
Efficiency in terms of
Efficiency in terms of the delivering services and improving the customer satisfactions in terms of the how much time they are in terms of delivery of product, at the same time the quality of things they are getting and resolving their concerns.
So see, you can't force people to deliver something faster, right? Like that is something we cannot do and we should not be doing. What happens is we give incentives that if you are driving without any, so there is a factor which takes into account how customer rated this delivery, right? So there are two parts of the rating. One is customer, like how the delivery was made and how the food was, right?
Yes.
So based on that, delivery partner is given incentive that yes, you made this delivery which the customer liked and you did it on time without any incidents. You either get some rewards, or you get some points, or you get some extra revenue, or you get extra tip, all of that. So you incentivize them in a way where it is leading to responsible behavior rather than, say, if I'm
Yeah,
optimizing
right.
for efficiency, right, they can start rash driving and then those things will come into picture, right? We have to be careful of that.
I guess that that should not come as a this thing irresponsible behavior of driving, and I do not want to convey in that manner.
Exactly. Cool. Recommendations. What should it be? Shadow or AB? Shadow plus AB. Okay. Can you tell me? Okay, shadow is not the answer. Okay. Can you tell me why? Why shadow does not make sense here? Exactly. We don't have the feedback available, so there's no point to even run a shadow, right? Because even though I'll make prediction, my model will work, but I wouldn't know how it is performing. So shadow is sort of useless here. Yep.
What I said, dummy data, or just try if you are very new,
Mhm.
to the like a startup or something, and you need data.
Mhm.
So for that, for some time you can use shadow, right, to get the prediction patterns, because as it is a log means something data is there.
Hmm.
So from same person you have two kinds of things, like you are generating the data also from the log and actual from
And
VB.
so for models like recommendations, let's say you said that for this user, show this user 10 restaurants, right? These 10. But recommendations are helpful only if we get a feedback, right? If user is not even able to give me what he or she likes out of those 10, what's the point of even running my model in an offline mode and logging it when I don't know the feedback? Well, I can always do that offline. Like right? I have that, like currently my one model is running. I'm already logging all of that. I can run my model offline and see how it gave, right? So I'm not getting any goodness out of running recommendation model in a shadow mode. Only goodness I'm getting is whether the endpoint is able to withstand that traffic or not. Okay, that's the only advantage. So shadow does not really make sense. Cool. So now let's come to data monitoring. So now you have deployed the model. Now we have to check, since models degrade data distribution changes, now there needs to be monitoring frameworks, monitoring pipelines in place to raise alerts before we even like go ahead with some new model or anything like that, because we might need to retrain or we might to refresh it. So for that, we'll first come to data monitoring. Now, usme, we have like some prerequisite knowledge that we should have. One is like, what are data stores, like different kinds of data stores. Simple is, one is data lake. Like you might have heard at it like this term at a lot of places. Data lake is just dumping all the data at one place, no filtering, no pre-processing, nothing. It could be images, it could be text, it could be tabular data, it could be anything, it could be even junk. Then data warehouse comes, where you process all the data from data lake and store it in a structured way. Like if it's image, you add all the metadata and all of that. If it's table, then you clean up all the tables, because it usually APIs generate data in a JSON format. Now you expand that JSON into rows and you create it in a structured format. That's where data warehouse comes. And then finally, feature store. Feature store is data warehouse. It's a structured and processed data, but just for MLs. The general pipeline is this: data lake has data, from data lake, data goes to warehouse in a structured manner. You do some feature engineering from data lake or from data warehouse, because not everything is in data warehouse, right? Images, like you will keep image metadata in data warehouse, but you will not keep image in a data lake. So for that, you will need it directly. You'll read that image directly from the data lake. You store this in a feature store, and then you use those features in a model, right? Now coming to the feature store, what feature store is. So let's step back a bit. If you guys are training a model and you have training like all the data, you'll create features right then from the data, right? You will do that because it's usually a one-off exercise. You train your model and then you'll finally like end it. Like for example, a Kaggle combination, right? Competition. You have a data, you create features, you train your model, and you get the final whatever output it is. In like when you're deploying a model for a use case, you will need to repeat that activity again and again, whether you're refreshing it, whether you are retraining it, whatever you're doing, right? You'll need to get that feature again and again. So Uber started doing this. They were the sort of first company, maybe like people were doing before that, but they were the first company who came out public with this, where they created a database table for features itself. Like you're computing them daily and storing them so that they can be directly used with your data and fetched into models. So you're not spending time on creating features, like they're already available. So and advantage of this is you're not the only data scientist working on these features, right? There are n number of data scientists, all of them are creating new features. So it becomes a repository very soon, a very big repository where you can just discover features which might already be there, which you were trying to calculate, or maybe something better which you didn't even think of, right? So this like feature store becomes a place to share and discover features, and quickly optimize, like everything is optimized, right? You can quickly create your offline pipelines and do this. And this feature, these features are point in time data. What I mean by that is you generate features every day or for every hour, for whatever timestamp, like whatever granularity you're working for, you generate those features, and there is no leakage sort of happens while training. Is everybody aware of what data leakage is in their pipelines? Okay, so let's say you are training a model, recommendation model, right? Let's say you do that. Now it's a sort of time series data, or let's not even consider recommendation. Let's just take time series forecasting. What usually happens if a model is not time series, you take the data, you do random split, you do cross value, whatever you're trying to do, and then you have some random part of the data as training and the remaining random part as test, right? Now there you have lost all the dependency between rows because you're assuming their IID, right? There is no time component there. So there you can do it, but in time series you won't be doing it because for a signal, what was the value today may be dependent on yesterday, right? Because that is what the time series forecasting tries to bring in. So you have that trend, and if you are using random data, it is possible that you have one out of 3 months, you have taken 1 month of data, and third month of data is training, and second month of data is test. But you, to your model, you have already told that model what the future looks like. So it knows, and it knows some part of the past as well. So it becomes easy for model to predict what was in the middle. This is called data leakage because you've already told model what it would be in future, and that's how, like, so in when there is data leakage, and data leakage can come in a lot of ways, but when there is a data leakage, you basically your model starts performing well on val data as well. But when you do it on unseen data, like out of, like, which was not of your training period or val period, it starts performing worse, and then you have to figure out why. So having feature stores removes that dependency to check whether you have the data leakage in your model or not, because you will be joining it directly based on dates, and based on that you will be training a model which will give you, like, ensure that you don't have the data leakage. So feature stores, you store it offline to be used in your offline pipelines. And again, latency, low latency retrieval comes when you have, let's say, online model, right? In online model, you will take features in real time and then compute whatever gradients you have to compute in the final score. For that, you'll use real time signals directly. And there again, so feature store also helps there. Like you can have pipelines which are pushing the features that you require directly to Redis, and then you have the whole thing working as a model. So feature stores work as both training time and as well as serving time, right? And this sort of decouples feature engineering and model training. So if, for example, Uber has another layer on top of their feature store where they run a automated feature engineering framework where they take all the features in their feature store and they start plugging them in the model, and they see which combination of the feature itself is working well for their model. Like then they don't even have to do feature engineering from their end because they already have that repository, right? So this it decouples this model training and feature engineering and sort of brings in a lot of goodness to the whole process. Now this is a typical demonstration. So let's say this is your data. These are customer orders, and this customer ordered from this merchant, and what this was the item and this was the things. So out of this, if you look at this table, for example, for this customer, within this data, he or she made 2 orders in the last 30 days, right? So this becomes your feature, like orders in the last 30 days, and this becomes your pivot. Customer ID is the pivot, customer ID is the key. So in your features, like this is one feature, and there could be n number of features just at customer ID level. There could be n number of features just at item description or item ID. There could be item ID here as well, item ID level. Or there could be another embedding based store where you have each token, and for each token, or you have generated for each item different embeddings, you're storing them, right? So each of these are features, And a combination of this feature is called a sort of feature store. So if you look at this for each customer ID, this is the timestamp which handles point in time aspect of the feature stores. And you have different features combined here, like amount, type, whatever. So this becomes your feature store, and there are multiple tables which are pivoted at different keys. It could be customer ID, it could be customer ID, comma, restaurant ID, it could be customer ID, comma, item ID, it could be just item ID, just restaurant ID. There can be n number of combinations. Depends on your imagination or your creativity, how creative you are with feature engineering and your model pipeline, right? So this covers feature store and what data there is. Now coming to data monitoring, why do we need data monitoring, right? So with time, distribution changes. There are multiple factors because of which distribution changes. For example, seasonality. With time, things change. There are different seasons, summers, rains, winters. Then trends change. With some time, something becomes popular. After some time, something else becomes popular. Then there are personal preferences as well. Like right now, you're liking some, let's say, non-veg. After some time, you start liking Chinese. After some time, you'll start liking some burgers, anything like Italian or whatever. So your personal preferences also change. So data is always changing. And the data you train your model on, that distribution is always constant. So your model has seen some pattern based on which it has trained that yes, this is how it should work. But since that assumption itself is wrong and data itself has changed, that model needs to be handled, right? Now, so that's why we need data monitoring to see when this structure changes and when do we like how do we quantify that it is impacting the model, and when do we refresh the model, because you can't just keep on doing it daily. There might be some use cases where you can do it daily, but if you can be efficient about it, then you will just do it for like when you are detecting some distribution shift, right? So there comes data drift check, where you check how the data is drifted from your training distribution to your current distribution. So underlying assumption is feature distribution, that was the distribution of feature that was in training is not same as it is now. So that's the assumption of data drift, and that's what it checks for, right? So there are multiple ways of doing it. Like for numerical, there is this Jensen-Shannon divergence or KL divergence, and for categorical L infinity, and both of these are of course based on hypothesis testing. So again, that comes that how statistically significant the difference is. So you do that. As an example, like for example, assume this orange curve is the real data, and this blue one is the noise that I'm randomly generating. And when I add this noise to my original data, this green curve is the one I get, right? So this becomes, so now I'm going to check my shift between orange curve and green curve. So this is middle curve, middle graph is the one that like I'm adding different noises, and then I'm checking how my KL divergence is varying and how my Jensen-Shannon divergence is changing. So that's how, like based on this score, if it is something that like there will be a threshold which works best for you. If there is a threshold and if it is statistically significant, you will raise an alert where you will see that yes, your data has shifted, and it should be something like it should trigger a training pipeline, something like that. You can have a lot of automation on top of that. But this is one way. There are multiple ways of detecting data drift. Another drift is like in this paper, what they say is that dimensionality reduction techniques are indirect detectors of data shift. That's what they use from another research who like which proved that this happens, and then they do dimensional reduction on their whole data, and then so this is not at feature level, this becomes at whole data level, and then they generate two separate distribution, and they do normal hypothesis testing, and they come up with the final statistically significant result whether data has shifted or not. So this was the data drift. Does anyone is there any question anywhere, anything? This one? Sorry?
As we can see, there is a very small change from the upper limit.
So
like-
that's, see, it's the, okay, take it. Tell me what's your question?
So the question is ki, suppose it is first and first from the top and the second topmost.
Mm-hmm.
So do they play significant role? Because as the
Do they?
play a significant role in data leakage or let's say data drift, because as we can see, there is not a major change. If we are
So-
comparing down to up, then it's okay. But
Uh-huh.
the
So this
alternates-
plot is just showing you how the actual divergence score changes. And of course, if it's that delta is small enough, and if you can keep up with that, and if your recommendations are not, or whatever, your model performance is not degrading enough, then of course you can keep up with it. Like you don't have to do it the moment you detect that yes, there is a small delta.
So what is the time frame or usually used in industry? Like it is human call decision, right?
Huh?
While monitoring, we just get the inputs, but
Uh-huh.
it's our call when we have to
Exactly.
take
It depends on use case. For example, I know in food, recommendation preferences don't change for a month or 15 days, right? So I can take that leeway. Like if my recommendations are not fresh for a month or for 2 months, it's all right. Whereas if there is ETA prediction, right? If there is distribution changes frequently, maps changing differently, then even small thing might matter. So it depends from use case to use case. So the model owner, whoever the data scientist is, will decide what the threshold is for him or her.
So even further, like I've seen that if we are not, we are ordering for a week or something,
Mhm.
and after 2-3 months we are not ordering, we are getting the recommendations
Recommendations?
heavily for like book something or you missed out
Uh-huh.
from Swiggy or
Uh-huh.
any app. So does it come from the monitoring part or does it come from the data history recommendation basically?
So see, recommendation is something, for example, if they are offline, they'll always remain you as a user, right? Remain for you there. So let's say you did not order for the last 2 months, and now you've come to the app. So today you will not see anything, right? You will not see good results because we haven't stored them for you. But the moment you visited, like that's the assumption we have made in our offline job, that if someone visits online or like the app, generate recommendations for them. So recommendation part handles that, but that nudge that you're talking about, that you should order this or you have not visited the app in some time, that comes from different business level metrics. So either notifications will cover that. Notification has a separate model itself, which will look at that. If it's not the notification, then there will be a product person who will decide that yes, these are the customers who are not coming to the app or doing anything, and we should nudge them towards coming to the app and do something.
You mentioned there are multiple models with notifications, recommendations, and all running in parallel. So if there is a data leakage, then how do we identify in which model it is?
Because every model has their own pipeline, right? Not all the pipelines are together. Like what?
Taking from the data lake, right? So and the features also are common. It is in the repository. So if there is problem in that, then how do we identify which?
It's the see, you can have a centralized version. So there has to be a data lineage. So that's what there is. Like there has to be a lineage where this was the raw data. From raw it was going to some process data. Then from process data it was going to model, right? So there has to be this lineage. This is feature store. So there has to be this lineage, and once there is this lineage, then you will have the alerting mechanism at this layer, and all the alerts will be raised for all the models which are using that layer, right? So that can be done centrally. If that is not the place, then it's the responsibility of the data scientist, because he or she was the person who used that feature in their model. So they have to be careful that their model is working well. So they have to set the alerts. Like there can be centralized infrastructure and centralized library for that, but they themselves will need to add an alert for that feature for themselves.
So also, as you mentioned, there are multiple features everyone is getting created.
Mhm.
So there will be many features which are not used. There will
Mhm.
be some features who are mostly used.
Mhm.
And how do we have to also keep monitoring that also, like feature list, or
You
that
only
is just
monitor what you're
storage?
using, right?
Okay.
And after some time, there are teams. See, you have to keep your cost down. Otherwise, people will just keep on adding features, right? If there is a feature which is not being used for quite some time, then there are teams to just purge them, purge the data, remove those features, and all of that. Any other questions on data monitoring, data drift, anything? Cool. Model monitoring. So just like data, we have monitored data. We also monitor at model level. So data distribution change, that is the input to the model, but output can also change, right? The relationship between what the input was and what the output is, that changes with time, as well as model also stops or degrades with time, looking at distribution and all of that. So the idea for model monitoring is that we need to be proactive, and uh, before someone else reaches out to us that this is not working, we fix it from our end. So there have been many escalations at Swiggy where customer comes to us then and asks that, for example, there's a widget called reorder widget, which basically says that this is the restaurant you ordered from, why don't you reorder from it? And we have significant traffic from that widget, and a lot of people are loyal to that widget. Now we have escalations from customers who come and say to us that they ordered from this restaurant yesterday and they expect this restaurant to be in this widget because it's a reorder widget, right? But they're not seeing it. So before that happens, before someone comes to us and asks us why it's not happening, model monitoring is there for us to determine, so that we can quickly fix that issue, so that no one comes to us and we're just giving good customer experience. And this was from the customer experience point of view. There are also infra scale up requirements. For example, during IPL or during New Year's, during festivals, traffic suddenly increase. Now, if I have not prepared my infra to handle that traffic, it can be automated as well, but we usually prefer not to have it automated. So yeah. So based on that, we decide to decide whether we need infra scale up or not, and based on that, we decide when to train, when not to train, and all of that, right? So different kinds of monitoring comes when we talk about monitoring. One is endpoint monitoring, and another is model or concept drift monitoring, right? So what is endpoint monitoring? Endpoint contains multiple things. Like, we discuss how the throughput is changing for the model. uh, by throughput, I mean per second, how many requests am I receiving for a particular model? Of course, this alert will help me to scale up and remind me whether I need to scale up or not. Then model latencies. Usually for every engineering system, you will have some latency requirement, right? For example, for homepage recommendation systems, we have a latency requirement of 100 milliseconds. Like within 100 milliseconds, our model should respond uh, with all the recommendations that a customer needs to show. Now, there needs to be an alert which basically talks about timeouts and long like delays in this latencies, because this directly impacts how the app loads. Like, app load time depends on these latencies, so it directly hampers the customer experience. So this alert needs to be there. Then similarly, model error rates. We have deployed a model assuming that model is going to perform well and model is going to return whenever it needs to perform. But with time, we can see if errors are increasing, then there is some issue, something else going on. Either model is not able to perform well, there is not like no training is happening, no offline job is pushing to anywhere. There can be a number of reasons. So model error rates. Then default feature fetches. Feature fetch is something, for example, online model, right? I am going to fetch all my feature values from my key value store, but when a feature value is not available, I use a default value because I need to use something, right? Now, if feature fetches increase in my model, like daily model calls, that means the actual feature value is not there. And if it's going beyond a particular threshold, uh, then that means that there is something wrong with the feature job, right? And if there is something wrong with the feature job, then I have to work on that. So one part of it could be caught at the feature level when you're doing data level monitoring, but if it's not caught there, then it should be caught here. So this is another of those fail safe things. Then model logging and output values are something that you do debugging and outlier analysis. So you log that and you monitor that. So that is there. Coming to model drift and concept drift, like I just model monitoring है उसके बाद like we can cool. Concept drift. So just like data drift, we assumed distribution of input data changes with the current input data. In model drift, whatever the distribution was for the label, like the y variable in training data, has that change with the current in the current setup. So that's what model drift checks for. For example, fraudsters keep changing their tactics. So previously, what was the distribution has changed to something else, right? So and again, so this is similar to how we are doing it for data. We take the training data set, we see what are the predictions are now, and we create a distribution and check for drift and see how it's doing. Another way of doing it is check for recommendations and see how the quality of predictions is. Not recommendation, it could be any model, how the quality is changing with time. So this is the general way that when you catch model drift, your model quality is going down like this, and when you're refreshing it, it will with time it will be going like this, and then you handle it, and then so it just like you refresh it and reaches at a level, and then again it starts degrading. So this is a cat and mouse game which keeps on happening. Another aspect of feature attribution, model monitoring is feature attribution, where you are trying to attribute which features are the ones which led to the model degradation. So I'll explain this. This is a public case study by Google, where they had this model running where this blue line, which was F6, feature F6, feature F6, whatever, feature F1 or F6, F1 F taken. Feature F1 was the best feature in their model, but on October 16th, it started degrading and it came down, because of which model performance came down, and they had the monitoring in place, so they quickly trained a new model where F4 and F6 basically replaced feature 1 and brought the same performance. But if they had not caught this alert on time, caught this thing on time, their model would have kept on reducing in quality. So this is the kind of things that we as data scientists, we need to check for, and we need to keep up for it. Sorry, y-axis is I don't know what this is, like they have not discussed. I'm just likely feature importance, something like that, but it could also be throughput. Actually it's saying I don't know, attributed some by feature name, maybe they have some so they come to this basically how they got it. So okay, I didn't know it could reach this level. So they have different ways of doing it. How do you check for these things, basically this score or what the importance of each feature is? So they use, like, most of you people must have heard of Shapely and Lime, like within explainability construct, but here they use it as a feature contribution of feature to the model, and based on which they get these scores and see the drift between these scores. Like they'll get the importance of each feature, and they see if there is a drift between this current value and the value before. So they use these techniques using different ways. So one is Shapely, integrated gradient, Slime, like all of the resources are there, you can go through them and come up with the final monitoring framework. So that's the, like, let's take a break here. Before that, if any of you have any questions in data and model monitoring, I'd be happy to answer. Depends on the data, yes. That is what we need to check. There would be drifts, but we need to check for them. So this example is that, like, a drift, for example, why this error came here is at the back end, F1, like the feature, the job that was generating F1, it stopped working. So the coverage, or it stopped working in a way, it was not producing as many results that it was. So previously, let's say it was creating 1,000 records. Next day it started only creating 10 records. So there was a gap in feature job. So this is sort of a drift, like not drift, but similarly there would be gaps because of the drift as well, right? This whole plot, like currently it is a line and then it starts degrading. Similarly with the drift, it will also start degrading. Hmm. 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 So you don't backtrack, like you can backtrack if you want to find the exact cause, right? The thing that you try to do at this scale is you try to detect if there is a reasonable drift and if your model quality is going down. The moment it starts going down and there's a, like, there would be a threshold till when you will be okay with that degradation. After, for example, this plot, right? So till this state, like I was okay when it was degrading this much. The moment it degraded this much, I retrained another version and started again, right? So it depends what you're okay with and how much you're ready to endure, sort of how much bad experience you're ready to be okay with. Well, it is never about backtracking. So it can be about backtracking if you really want to add it as a feature. Maybe the actual behavior also changed, right? That can give you an information towards adding a new feature. So you can do backtracking for that, and backtracking, like a normal way would be you will look at the feature, you will see that this distribution has changed and that's why your quality of model has changed. Then you look at that feature and see exactly how it's being computed, and then you will go back further and see what exactly is changing, like where the distribution is changing, for which customer it might have changed, what was that customer's history. So you have to get your hands dirty with data. There's no automation. So you can build one if you if you are able to. Cool. This was model monitoring. Any questions? Anything? Cool. Let's take a break.